Okay, so in this lab we're going to talk about how to perform a two-way ANOVA to study the joint effects of two different factors on a response variable. And I'm going to go over two different examples of this and show you both how to incorporate those potential interaction effects that we talked about in the lecture and how to write models that don't incorporate those interaction effects. And then we'll talk about the difference between them. Now, all of the examples we're going to talk about today involve factorial two-way ANOVAs, okay? And so what this means is by a factorial design, we're talking about a design where we have observations for all possible combinations of the levels of the factors we're investigating. Okay, so if we have two factors that each have two levels, that means there are four possible combinations of those two factors. And so you'll see what I mean in just a minute. So our first example is we're going to study the effect of elevation and aspect on tree size, in this case height. And so the experimental design is that we had trees that were experimentally planted at two different elevations, low and high elevation. Okay, so elevation is our first factor, and on two different aspects of the mountain. So on the north-facing slopes and on the south-facing slopes. So what that means is that we have 20 trees that were planted in the low elevation north-facing slopes, 20 trees planted in the low elevation south-facing slopes, and then 20 at the high north slopes and 20 at the high south-facing slopes. Okay, this allows us to then ask, what is the effect of aspect and elevation and possibly their interaction on tree height? Okay, so I'll start by reading in my CSV file here, and I've saved this in the trees aspect elevation CSV file. Okay, read that in. Oh, actually, I need to make sure I set my working directory to the right place. Okay. I'll read that in. Let's take a look at the first 5 rows of this file. Okay, and I have 3 different columns. I have my aspect column, that's my first factor, my elevation column, and my height column. Let's just for good practice, let's take a look at the structure of this data frame. Okay, so aspect is a factor. It has, that's not good. Okay, so I see that it's telling me it has 3 levels. It has this blank level, north and south. I don't want that. I don't want this blank level in there. And then it has this high and low elevation, and it also has this blank for elevation. Let's see. So sometimes, actually, let's just take a look. I'm going to take a look at my data frame here. Okay. I'm just going to scroll down. I don't have tons of observations, so I can just do this manually. Okay, and I see here that, yeah, so row 81 here has sort of read in incorrectly. So sometimes this happens with a CSV file. If you accidentally put a space or something in an empty row, then it reads that in as an actual data row. I don't want that, because what that's now doing is it's treating north, south, and then this blank as a third factor level. I don't want that. So I just want to delete this whole row. So I could do this in one of 2 ways. The first way I could do it is to actually, in R, just erase this 81st row, and then I would need to reassign the levels of these factors to make sure that I get rid of this empty factor level. Okay. The easier way to do that is I'm going to actually go into my CSV file and just clear that bottom row. So I'll show you how to do that right now. I'll go to Documents, go into my folder that I have this file saved. Okay. Tree aspect elevation.csv. I come down to this row down here. Okay, and I see right here, so I have an extra blank space there. I don't want that. So I'll just grab a bunch of these rows at the bottom, right click, go delete. That just clears them, okay, completely. Now I'll just click save, and I want to overwrite. Okay, come back to my file. So let's read this back in now. Okay, and then I can take a look at my head, my structure. Let's take a look at the last 5 rows using this tail function. Okay, and I can see now there's no 81st row. So actually if I click on this again, and I I scroll back down. Now that I've deleted or cleared all of these rows down here in my CSV file and then resaved it, I can see that when I read it back into R now, it's not picking up that extra row that I didn't want in there. Okay, so I have the data file read in correctly now, and everything's going to work. Well, in theory at least. So, okay, well let's then just take a look at the data with some box plots. So I'm going to go box plot, tree, $heights. Let's just take a look at the distribution of heights for all the observations, all 80 observations. Okay, so I see that tree heights range from like about 0.12 up to 0.35. That looks pretty normal in general. Can't really tell that from a box plot again, but it does look like the median is right in the middle of the interquartile range and the whiskers are about the same length on either side. Okay, that looks pretty good. Let's take a look at box plot. Now let's look at height as a function of both aspect. Well, first let's just look at box plot as a function of aspect. Oh, and I need to specify my data frame is tree. Should work. Okay, so I see here it's not exactly clear if, it doesn't really look like there's an effective aspect so far. But again, we know that half of these trees in the north aspect are in the low elevation site and half of them are in the high elevation site. And so that there may actually be a hidden effect of aspect that is masked by the fact that elevation is also affecting our response, okay? So let's just for fun, let's take a look at the effect of elevation here. Okay, so there's a clear effect of elevation in this case. Now let's take a look at the joint effects of height and elevation using our box plots. Oops, I mean the joint effects of aspect and elevation on height. Okay, so I do that by specifying aspect, and then I also want to include separate box plots for elevation. And so what this will do is plot 4 different box plots, one for each combination of aspect and elevation. Okay, so I run this. And so what I see here on the x-axis is my 4 different experimental treatments now. So I have my distribution of tree heights in the north aspect high elevation sites, my south aspect high elevation sites, my north aspect low elevation sites, and my south aspect low elevation sites. And so looking at this, it looks like if I compare north and south, okay, so north versus south and north versus south, it looks as though the north aspect tends to have higher tree heights, larger tree heights than the south aspect, okay, in both cases. And it looks like my high elevation sites, so these 2 box plots, tend to be smaller on average. Okay, they have a lower response than these 2 box plots, which are my low elevation sites. Okay, so trees, looks like trees tend to be bigger at low elevations, and they tend to be bigger on the north-facing slopes. Now, if I had to guess just by looking at this plot, I'm going to guess that the interaction between aspect and elevation is not significant, okay, because it doesn't look like the effect of aspect depends on our elevation. Okay, so the difference between north and south aspects doesn't look like it's any different in the high elevation or the low elevation sites. It looks like in both cases, the south aspect is about, I don't know, like 0.5 or something lower than the north aspect. Okay, but we'll create some models to take a look at that statistically. So we'll start off by creating a model without that interaction term in it. Okay, so all we're looking at is what's called the additive effects of aspect and elevation on tree height, but not their interaction with each other. Okay, so to do that, I'm going to create a linear model, LM. I'm going to treat height as a function of aspect and elevation, specify my data frame, and then I'm just going to store that in an object. I'll call it tree.lm1. Okay, I'll run that. And now let's take a look at our summary statistics for tree.lm1. Okay, so what these summary statistics tell me is that overall my model is statistically significant, okay, very significant. So there are significant differences between trees grown under these different treatments, and I can see that pretty clearly from these box plots. More importantly now, I want to take a look at my coefficients because this tells me more about the effect of aspect and elevation on tree height. Okay, so my baseline condition in this case is going to be north-facing aspects and high elevation. Okay, and I know that for two reasons. One, I can see that here in my coefficients table that it's telling me what is the effect of south aspect. So that's going to be the effect of south aspect relative to my baseline. So that has to be relative to my north aspect. And what's the effect of elevation low relative to my baseline? So that means my baseline has to be elevation high. I also know that from looking at my box plot over here. Okay, north and high are furthest to the left. So that means that R has automatically assigned those as the lowest levels, the baseline levels of those two factors. I could also check that by going levels of tree $aspect. When I run that, it tells me north is my first level, so that's my baseline, and then south is my second level. And I could do the same thing for tree.elevation, tree $elevation. Okay, so my high elevation sites are my baseline, and low elevation is that other level of that factor. Okay, let's go back up here to these coefficients. So this tells me that the intercept of my model is 0.195. So that means trees grown in my north-facing slopes at high elevation, okay, my baseline. So when both of my factors are at their lowest level, north and high, it's estimating that the average, the mean size of trees for that treatment is 0.195. Next, it's telling me, okay, well, what is the effect of aspect on tree size? And so that's negative 0.017, and that's statistically significant. This p-value is less than 0.05. Okay, so 0.015, that's pretty low. It's not extremely low, but it's pretty low. And so that tells me that aspect has a significant effect on tree height. And I can see that from this, the south-facing slopes have a slightly lower mean size because this coefficient is negative than north-facing slopes. Okay, so to calculate the mean size of trees on south-facing slopes and at high elevation, I would take 0.195, subtract 0.017807. Now it also tells me the effect of elevation, low elevation. So trees at high elevation and north-facing slopes have 0.195 as their mean size. At low elevation, I then add 0.094. Okay, so this tells me that low elevation has a positive effect because it adds to my intercept. Okay, negative values mean that the mean size is lower under this condition. Positive values mean that the mean size of trees is higher under this condition, okay, under low elevation. So I can see that from these box plots. My north-facing sites have a much higher mean tree size than my south-facing sites. Okay, and my low elevation sites have a much greater tree height than my high elevation sites. Now, if I wanted to calculate the mean size of trees at my south-facing sites and my low elevation sites, what I would do is I take 0.195, then to get the effect of the south-facing slope, I subtract negative 0.0178. And then on top of that, to get the low elevation effect, then I add 0.094. Okay? So basically, since my intercept is my north and high, I first want to switch my aspect to south, so then I subtract 0.017, and then I want to switch my elevation from high to low, and so then I add 0.094, and that would give me a value somewhere around here, around 0.28. Let's just try that down here. So 0.195 minus the effect of my south-facing slope, and then I add the effect of my low elevation. around 0.27. Okay, that seems like that's about where this box plot is telling me, just looking at my data. Okay, so what these coefficients tell me, just to recap, is that there's a significant effect of both aspect and elevation. I can see that from this p-value, and that south-facing slopes tend to have lower tree sizes on average, and that low elevation sites tend to have larger tree sizes on average. Now in this table, I haven't yet investigated the effect of an interaction between aspect and elevation, okay? And that's because I included this plus sign in my linear model. Now we're going to take a look at what happens when we include that interaction and test to see if that interaction actually is statistically significant. So does the effect of aspect depend on your elevation? Now to do this, I'll just create another linear model. So I'll call this tree.lm2. It's going to be a linear model with height as a function of aspect, just as it was before, but now I'm going to do times, or asterisk, elevation. Okay, this tells R to automatically assess the effect of aspect and elevation and their interaction with each other on tree height. Okay, I'll run this. Let's take a look at the summary statistics for this model that I've created, tree.lm2, to see if this interaction is significant. So take a look here. Okay, so looking at my coefficients, I can see again my intercept. So this is my baseline condition, north aspect, high elevation. I can see that aspect has a negative effect on tree size. And now that I've included this interaction term, it's changed my p-values in my model. So this p-value is greater than 0.05. It used to be the p-value for aspect previously in just my additive model, let's go back up, aspect, was 0.0155. Okay, we usually consider that fairly statistically significant. Now it's greater than 0.05, okay, so that's pretty marginal. Elevation still has a strongly significant effect on tree size, okay, and low elevation sites tend to increase tree size because this coefficient is positive. And here's the interaction term, okay, so what happens when you have both south and low elevation sites together? And the interaction term in this case is not statistically significant, okay, this is an extremely large p-value, almost 1, okay. And so what this tells me is that the interaction between aspect and elevation is not statistically significant. So in this case, if I wanted to actually interpret my coefficients and arrive at decent estimates of mean tree size in each of these different treatments, I might actually just go with my first model here, okay? So this second model was useful because it tells me that this interaction between aspect and elevation is not statistically significant. Now if I want to actually get good estimates for what are my mean tree sizes under each of these different treatments, I might then go back to my first model where I only include this additive effect and I leave this interaction term out, okay, because it's not statistically significant. I can see that overall the whole model is statistically significant, and that's because it includes these significant terms in it, okay, the effect of elevation and the marginally significant effect of aspect, okay. But my first model, tree.lm1, included significant terms for aspect and low elevation. The whole model was significant, and it doesn't include that sort of insignificant, unparsimonious interaction there. Okay, so if I was to write my conclusions from this model then, I would conclude that based on my models, aspect has a somewhat significant effect on tree size. Okay, and I would also say that south-facing slopes are slightly, the trees grown on south-facing slopes are slightly smaller than trees grown on north-facing slopes. And second, more importantly, I would say that elevation has a very significant effect on tree size. And I would say that trees at low elevation are much larger than trees at high elevation. Okay, and that's because this low elevation term increases your mean tree size. And then third, I would say that the interaction between elevation and aspect is not statistically significant. Okay, now as I mentioned in the lecture, R has automatically assigned the levels of my factors, okay, and by default it goes alphabetically. So since north is alphabetically first relative to south, that means that north will be my first level of my aspect factor, and since H comes before L, this means that high elevation sites will be the baseline relative to low elevation sites. But I might not always want that. I might want to reorder this so that maybe I still want my north aspects to be my baseline, okay, in terms of aspect, but I want a different baseline in terms of elevation. Okay, maybe I want low to be my baseline, and then I want my coefficients to tell me what is the effect of high elevation relative to low elevation. And so I need to reorder my factors in order to do that. So the way I would do that is I just take my tree data frame and my elevation column. I'm going to specify that that's a factor. Okay, it already is. But then I'm going to set the levels. And the levels here are going to be, first I want my low elevation. Okay, low comes first now, and then high. Okay, so now I've reordered them. So I run this. It doesn't look like anything's happened. If I take a look at my data frame, it's going to look exactly the same. But now let's go ahead and try running first. I'm just going to copy this down here. First, let's run this box plot command. Okay, it's going to plot the exact same thing, but now it's going to reorder these boxes. Okay, because low now should come before high. Okay, so my north aspect is still my baseline, but now low is my baseline elevation. Okay, low comes first, and then my high elevation sites come second. Now, if I was to rerun my model, so I'm going to create, I'm just going to copy this tree.lm1 here. Okay, I'm going to call this tree.lm3. Okay, because I just want to preserve lm1 as a comparison here. So this is the exact same model as lm1. My p-values will all still be exactly the same. The difference now is that my coefficients will be different because I have a different baseline against which I'm comparing all my different treatments. Okay, so I'll run this tree.lm3. Let's take a look at it. And just for comparison, let's pull up a summary of tree.lm1. Okay, so let's start by comparing the p-values in tree.lm3. So again, the difference between lm3 and lm1 is just that I've relabeled my factors so that low comes before high in lm3. In lm1, high comes before low. Okay, I can see that my p-values here are exactly the same. Let me just make this a little bit bigger. Okay, my p-values up here are exactly the same as my p-values down here. I can see that my coefficients are slightly different now. Okay, so in my LM3, low is my baseline. Okay, low and north-facing sites are my baseline. And then it tells me what is the effect of high elevation relative to my low elevation sites. Okay, so this tells me the mean size at my low elevation north-facing sites, 0.289. If I look at that, yep, that looks about right. Okay, south aspect reduces tree size, and high elevation reduces tree size relative to my low elevation sites. Okay, and we compare that back to my first model where my high elevation sites were the baseline. Okay, we see that low elevation increases tree size relative to high elevation. Okay, so these models are telling you the exact same thing. They have the exact same R squared, the exact same p-values. The only difference is what is your baseline condition against which you're comparing everything else to. Really, this is just a different way of presenting the exact same thing. Okay, and it's just your own preference or your own ease of interpreting your results will determine how you want to relabel and reorder the levels of your factors. Okay? If you prefer to interpret everything as in relation to your low elevation sites, then you may want to set your low elevation to your first level of your factor, and then your high elevation is your second level, and then everything will be read in relation to your low elevation sites. All right, so let's go on to a second example here. This is the effect of drug dose and sex on the phosphatase levels in dogs. And so here we have alkaline phosphatase level was measured from blood samples in order to screen for toxicity problems. Okay, and so we want to investigate the interaction, the potential interaction between two factors, sex and dosage. So here, this is telling me I want to read in the dog's data set, visualize the data, and then perform a two-way ANOVA with an interaction. So let's start by reading in my data. Let's take a look. My data is dogs.txt. It's a txt file, so I need to use read.table. Okay, dogs.txt. Let's go dogs. We'll just call this data frame dogs. Read this in. Actually, let me start by clearing my working directory. Okay, read in my dogs data set. Let's take a look at the first 5 rows. And, okay, so my first row has my column names, so I need to actually, let's just take a look at the help file for read.table really quickly here. I need to specify call.names. Call.names equals true. Okay, let's run that again. Oops, nope, I need to specify header equals true. Okay, run that. Okay, now it's correctly assigned the names. Let's just take a look at the structure of my data. Okay, sex is a factor with 2 levels, F and M. Dose is a factor with 2 levels, dose 25 and dose 8. Okay, and so if I take a look at the levels of dogs $dose, I believe it's going to tell me that dose 25 is my first level and dose 8 is my second. 8 is a lower dose than 25, so I'm just going to reorder these factors. So let's go dogs dose is going to be factor, dogs dose, and I want my levels. I want dose 8 first, that'll be my baseline, and then dose 25, that's the higher dose. I want that as the comparison group. Okay, run this. Okay, so I have read in my dogs data set. Let's visualize the data. So I'm going to go box plot. I'm going to level is my response, and I want to visualize the effects of dose and sex. Data is dogs. I'll run this. Okay, so I can see that dose 8 and females are my baseline. Now it looks like if I increase the dose to 25 for females, that seems to increase the levels of phosphatase. Now here, if I stay with dose 8, but I change from females to males, okay? So if the sex is male, it looks like just in general, males have a much higher level of phosphatase under dose 8, okay? Dose 8 female, dose 8 male. Looks like sex increases my level of phosphatase, but if I compare dose 25 females to dose 25 males, it looks like males have a much lower level of phosphatase, okay? So this to me looks like there's an interaction going on. So if I increase my dose from 8 to 25, that increases my response for females, but it decreases my response for males. So that's sort of a classic interaction. And I'm going to explore that using a linear model. So I'll call this dogs.lm, and I'm going to specify I want a linear model. My level is going to be a function of dose times sex. Specify my data frame. Okay, let's run this. And now let's look at my summary statistics. Okay, and what I see from this, let's just make this a little bit bigger, is that I have significant effects of dose, I have significant effects of sex on my response, and I also have a highly significant interaction term. And that's not surprising given what we just saw from the box plots. Okay, my overall model is very significant. My R-squared is pretty high. That means I'm explaining a lot of the variation in my data, so that's pretty good. Okay, now let's go ahead and interpret this a little bit. So my baseline condition has a level of 133.5. Okay, my baseline is dose 8 in females. Okay, and I can tell that because dose 25 is my first coefficient here, sex male is my second, so I know that my baseline must be the opposite of sex male, that's sex female, and it must be the opposite of dose 25, so that would be dose 8. Okay, so females that have a dose level of 8 end up with a response of 133. Now for females, if I increase the dose to 25, then I would add 32 onto their response. Okay, so I can see that here. If I go from 8 to 25 for females, that increases their response. Okay, increases their level here. If I go from females to male, but I leave my dose unchanged, okay, female, and now I just switch the sex to male, that increases the response by 47. So I go from my baseline, and now the only thing I switch is male, that increases the response by 47. Okay, and that's statistically significant. Now finally, if I want to see what is the effect for males with that higher dose, I do two things. So I take my baseline, I change my dose to 25, so I add 32. I change my sex to male, so I add a further 47 onto this quantity. But then I also add on the effect of this interaction. So I subtract 141.25. Okay, and so I can see here that if I was to do that, let's just do that right down here. 133, okay, plus 32 plus 47. Okay, so that's the effect of male sex. And then now I subtract 141.25 because when you have both a dose of 25 and you have a male sex, this interaction is significant, so it subtracts 141 from your overall response. And that means that my overall response for males with a dose of 25 is 71.25, okay? And that's much lower than my intercept here. So this is a significant interaction happening. The effect of dose depends on your sex. Okay, so if I was to write out my conclusions, I would say that firstly, higher doses increase the response. This is what we call levels in the data frame for females. And actually, we could even get a little more specific by 32. Okay? Because I can see here that if I increase the dose to 25, that increases the response by 32. And this is highly statistically significant. Well, I wouldn't say highly statistically significant. This is barely statistically significant. Okay? It's just barely lower than 0.05. That's a pretty low threshold for statistical significance, but we'll roll with it. Okay, next we would say that males have a higher response than females, but only at a dose level of 8. Okay, so this is relative to my baseline. Males have a higher response because this coefficient is positive. And we can see that from the box plot. Now lastly, there is a significant interaction between dose and sex. And what this means is that higher dose levels decrease the response for males, but increase the response for females. Okay, I can see this from my box plots, but I can also calculate that numerically by adding or subtracting these coefficients. Okay, so those are just two examples of multi-way ANOVAs, two-way ANOVAs, where we can investigate whether these interactions are statistically significant or not. You can include more factors than just 2, so you could have 3 or 4 or 5 different factors as explanatory variables in your model, okay? But if you start including more and more interaction terms, you can probably imagine how that can quickly become really, really hard to interpret. Okay, it's hard to plot it even in more than 2 dimensions. And when you begin to have these 3-way interactions, so if you had a third factor here, and let's say we had another one that was the interaction between dose, sex, and, I don't know, like color or something like that. Okay, we have this 3-way interaction. It's almost impossible to interpret. So usually you want to try to avoid including 3-way interactions, but sometimes it does make sense to include many different factors in your models. It all just depends on your question.